show how you would accomplish the following synthetic conversions. 3-methyl pent-2-ene to 2-chloro-3-methyl pent-3-ol. Okay, so right here we have a methyl pentene, right? Okay, and that right there is a double bond, isn't it? So we look at the options and we go, well, they're all the same. We have a double bond. Cool. The next thing we do is, well, we've added what to this? We've added a chlorine, right? We've also added an alcohol. Okay. So we have to add two things to this, don't we? What are those things going to be? Well, they could be chlorine and an alcohol, right? So automatically we know anything that doesn't have chlorine and alcohol in it, or an alcohol. Does anybody know what the simplest alcohol is called? Water. Water is the simplest alcohol, okay? So we can look for water, right? We need chlorine, we need water. Some way, somehow. None of these other things have chlorine or water, right? This could do the OH, couldn't do the chlorine, could it? This couldn't do either of them. You literally don't have either thing you want to add on there, do you? Okay? This could do a chlorine, couldn't it? We could do that same Cl2 attacking. And then we have waters. Well, you remember the water attacking a carbocation, don't you? That loses the proton. Yeah, that makes sense. That could do it. And yeah, that couldn't even do that at all, right? Doesn't even have the groups. Okay. So we really only have one thing at all that would even make any sense, right? Because the rest of them couldn't even put a chlorine and a hydroxide on, or an OH on. So, okay. Chlorocyclohexane to trans 2-chlorocyclohexanol. All right, so we need to go from the chlorocyclohexane to a trans 2-chlorocyclohexanol. But, that's going to require getting an alcohol on there, isn't it? And somehow getting that chlorine on there to stay. Or to add a chlorine back on, right? Okay. So, well, you have some options. There was you could try to do a substitution, but you wouldn't get both groups on, would you? Yeah, if you try to do a substitution, the name self-tells you, doesn't it? It's a substitution, you substitute. So you only get one group on. That's not going to work, is it? So we need to take a step back here. Okay, so what do we have that can do these things? Well, let's see. We know elimination reactions, we know substitution reactions, and we know addition reactions, right? We don't have a double bond to add on to, do we? No. So we can't do an addition yet. But we could do an elimination, couldn't we? That would give us a double bond, and then we could do an addition. And notice, we just did something that looks a lot like this, don't we? We have a Cl next to an OH here. So we've just seen the addition that could do this. Whoa, huh? Okay. So the best way to do this is you're going to need to go ahead and do an elimination first, right? You need to establish your double bond. That way you can go ahead and do the reaction to put these things on. Okay? Again, the reasoning there is you can't do a substitution. You can't do an addition yet. You only have one option left, don't you? You just have your elimination reactions. You don't know anything else yet. Okay, so use the tools you have available. Elimination it is, right? How do you do an elimination reaction? Well, these all share the same damn thing, don't they? So you have to do an elimination reaction no matter what you do, don't you? No matter what you select, you're going to get that. So really, the only thing we're actually evaluating here is this stuff, right? After this first step. First off, does this even make any damn sense? You have a Cl, and where the hell to go?
Somewhere else.
Yeah, I mean, that doesn't even work, right? It doesn't work with everything we know of science. It needs to go somewhere. We have an H2SO4, and it does exactly what? Nothing, right? I have no idea what that does, right? See, it doesn't do anything. You have an OH, and you get a double bond, but yeah, this doesn't have any purpose in this. So that doesn't make any sense, does it? Okay, so we have to stay to the things that make some sort of sense. We have two options here. And so we have the option where we have the double bond, and then we have the Cl2, H2O coming across it. And that looks just like the thing we just did, right? Okay, that's nice. And then it'd have plus an enantiomer here. And the other option would be the Cl2, same thing, same reaction. It's just the only difference here is we don't have anything saying plus an enantiomer, right? Okay. In this reaction, does it attack from one side and both things add from one side? So all in one step? Or is it going to attack one and then attack the other? So in other words, are we going to have the flip? Are we going to have the one where this is going away from us and this is coming towards us? Yeah, we have to, don't we? Yeah, because they don't happen all in one go, do they? It has to happen in two stages. And that means we're always going to have to make the two different options, right? Can you understand that and see that? Yeah. This first time, it doesn't matter what carbon we go on, does it? We're always going to get, half of them go on there, half of them go on there. And it doesn't matter which side we go on, does it? So we're always going to get, one's the top, one's the bottom. And that means we always get the other enantiomer with this. We're always going to have the opposites. That making sense? Fantastic. These are different groups, by the way, and so it's not symmetric anymore. In case I'm heading off anybody that went, wait, what about the one with the two CLs and they were on opposite sides? And you said they're symmetric. This one's not symmetric, is it? It's a CL and no H, right? So they're different. Okay. Anybody have any questions about that? No? Fantastic. 1-methyl cyclopentanol to 2-chloro 1-methyl cyclopentanol. Okay, so again, we're going to have to add some groups across this. That means we're going to have to probably do some form of elimination, aren't we? Because you won't be able to get 2 more groups onto this with a substitution, and we can't do an addition yet, can we? Yeah. Also, you don't really have any choices. Again, it always gives you the elimination product here, doesn't it? Yeah. So what we're really looking for is what would give us that elimination, right? Is this going to be an acid elimination or a base elimination? So, and that one doesn't even make sense, does it? The Cl2, does anybody have any issues with me just going, that doesn't make any sense. There's no CLs here. Doesn't do anything. Okay, so will a base give us a double bond? So if we had a base come along here, what would it most likely deprotonate? The OH, right? It's probably not going to deprotonate the carbon, is it? Yeah. And so that's probably not going to give us what we want, right? It would be very unlikely in this case to give us the elimination. So what we're looking for is probably an acid, right? And that actually, full stop, we're done. Yeah, because, there's no other acid one. They all have the base here, don't they? Yeah. Okay. Anyways, The difference is here for these other ones, by the way. So we make our wonderful little elimination product, the double bond, right? And then we end up using that same mechanism we've used in all these other ones. The Cl2 with the water, right? And that will give us our OH next to the Cl again. Again, they'll be on opposite sides. And because this doesn't have any geometry here, this is going to end up being an antimerge, right? Okay. Does anybody have any questions about this? No? Okay. Okay, fantastic.